Hello everyone. We're going to start introducing how to deal with linear systems of differential equations, in particular homogeneous ones. And I decided that I would do the first video on this topic not in just terms of, well, if we look at anything and what if we just look at it in general, but I'm actually going to look at very specific, easier examples where we're just working in two variables, for example x and y in terms of t. And then we'll just expand the ideas to three variables, and you can think about going beyond that. So we'll just begin working with this. So when we say homogeneous, we mean when we have the derivatives of, let's say, our variables x and y in terms of t equal to just expressions that are linear in terms of x and y. So we don't have any t terms on the right-hand side yet. We'll get to those maybe several videos from now. So we just have dx dt and dy dt in terms of x and y. So I've written a system here. We have dx dt is equal to x plus 2y, dy dt is equal to 3x plus 2y. And so let's just look at first how we would write this in the matrix form. So we could go ahead and write the left side of the equation basically as a column vector here, with dx dt being the top entry and dy dt being the bottom entry. And that would be equal to, so if we remember our matrix multiplication, we could look at just the coefficients. So we have 1x and 2y in the first row, and then we would have 3x and 2y, that's our information in the second row. And so that is going to be times our variable vector. So this is a column vector here with x and y in it. And so remember, as we take the first row, the 1 and the 2, we would multiply it by the x and the y and add those, and that would give us our first row. And then when we take the 3 and the 2 and multiply by the x and y, we would get the 3x plus 2y in the second equation there. So a way you'll see this abbreviated, rather than having to write all of this out, we will just call maybe the column vector that has all of the derivatives in it, we will call it capital X prime, is the way we usually see this, equal to, and then here A is generally what they call this. So this is it's usually a square matrix. It's just our coefficient matrix basically. And then the vector that has our variables in it will just be, we'll just call it capital X. So you can certainly see how x prime and x are related. X is just our variables, in this case xy. X prime is dx dt, dy dt. If we just want to verify, let's say we're solving, or maybe we're just starting out, we want to verify that something is solution for a system. So here I've got, we're going to show that x equals 2e to the 4t and y equals 3e to the 4t is a solution to the system that we have here. So really what we just need to do is, if we have this information, we have stuff for x, we have stuff for y, we just need to figure out, okay, well, if x is 2e to the 4t, then what is dx dt, right? So if we take the derivative of x with respect to t, then we'll get exponential derivative being itself. We'll have the chain rule pulls out a 4, so 4 times the 2 would give us 8e to the 4t. And then for y is 3e to the 4t. We're claiming that this is going to be a solution. So then the derivative of y with respect to t, same thing here, chain rule would give us a 4 comes out, times the 3 would give us 12e to the 4t. And then we can just plug all of this information over here into our equation over here, and we should get true statements. So for our first equation right here, dx dt, so dx dt we have 8e to the 4t is equal to x plus 2y, so x is 2e to the 4t, plus 2 times y, so 2 times, and y is 3e to the 4t. Okay, and if you simplify the right-hand side, you'll see you'll get 8e to the 4t is equal to 8e to the 4t. So that certainly works. And to make sure that the second equation works, so we look at dy dt, which is 12e to the 4t. And that would equal 3x, so 3 times 2e to the 4t, plus 2y, so 2 times 3e to the 4t. And when we simplify the right-hand side, we see that both sides say 12 times e to the 4t. And so certainly, since when we plug in x and y and their derivatives into the system and we get true statements for all, then this would be a solution for the system. Now it turns out there are many solutions for the system, but this is just a solution that works for this. So let's do one more. So now I've proposed two solutions. So I have a solution 1 here, where x is e to the 2t and y is 2e to the 2t. And then I've proposed a second solution here, where x is e to the 3t, y is also e to the 3t. So let's look at the first one. So if we do that, so let's look at dx dt. So dx dt for our first one would be 2e to the 2t, if we take the derivative of x, equals 4 times x, which is e to the 2t, minus y, which is 2e to the 2t. Okay, you can see that we have 4 of these minus 2 of these, so that's going to work there. And let's check the dy dt. So still checking the first solution here. So dy dt is going to be 2e to the 2t is our y, so the derivative would be 4e to the 2t, equal to 2 times x, so 2e to the 2t, plus y, and y is 2e to the 2t. And you can certainly see we get 2 of these and 2 more, that would be 4, so this works out as well. So you can see our first option here is a solution to that system of differential equations. And looking at the second one, so we'll look at our second option here, both of them are e to the 3t. So then dx dt is going to be 3e to the 3t, equal to 4x minus y, so 4 times x, e to the 3t, minus y, which is also e to the 3t. So you can see 4 minus 1 of them would give us 3 of them, so that works. And then we'll check the dy dt equation. So dy dt would also be 3e to the 3t with our second option, equal to 2x, so 2 times e to the 3t, plus y, and y is just e to the 3t, so you can see again 2 of these plus 1 of those is going to equal 3 of those, so that checks out as well. So these are both solutions for the system of differential equations we have over here. And it turns out that these are not just the only two. In fact, if we look at either of these, option 1 or option 2, any constant multiple of those expressions will also be a solution as well. So as we start moving toward solving these equations, so we'll have some system of differential equations, whether it's written out one way or the other. And the idea is if we have n variables that depend on t, so here we have x and y, so in the cases we've been doing so far this is 2 variables, right? So if we have n variables, then it turns out that what we'll get is we'll get a set of n, so the same number. If we had 2 variables, it would be 2 solutions. If we had 10 variables, 10 solutions, right? A set of n solutions. And those solutions are going to be what we have called before in some of the videos linearly independent. Right? Meaning that we can't take some multiples of a solution, some multiples of another solution, and combine them together to get some multiple of maybe a third solution or something like that. So there's no way to combine multiples, basically, of other solutions to create one of the particular solutions when we say they're linearly independent. Okay? And what you've seen in the last 2 examples, really, so our solutions have been in the form. Basically, I'm going to go ahead and call this x is equal to some constant, and some other constant times e to some multiple of t. Okay, so when you looked back at the last one, we had let's say x was e to the 2t and y was 2e to the 2t, so they were both some multiple of e to some multiple of t. Okay, so this little character here that we see in a lot of books, maybe not all books, but this is a Greek letter, lambda. Okay, and lambda is just a constant. So I think before we were calling it m, but in general in most texts you will see it as lambda. So if we, like we said before, so if we have two variables, then that means we should have a set of two solutions that are linearly independent. So if we have, let's say, two variables, we would have an x1, so that would be some solution. So we have some constant for x, maybe some constant for y, and that would be times e to the lambda, I'm going to call this lambda 1 times t, so e to the some constant times t, and then we'll have another solution, we'll call it x2, and that's going to be, so we'll have some constant for x and some constant for y, and that'll be times e to maybe some other multiple of t. We'll call that lambda 2. And so these values for lambda are going to be very important and allow us to solve the systems eventually. In this video, since it's just an intro, I'm not going to do actual direct solving of systems, but I just want to give you a real quick, hopefully clear explanation of why we do what we do when we solve systems. So the idea is we want to, basically we said we want to get something as a solution in the form x is equal to some constant that belongs to x, some constant that belongs to y, so we'll call that k1, k2, e to some lambda times t, okay? Or I'm actually going to go ahead and just call, so we don't have to keep writing this k1, k2 here, so we'll have some vector of constants, I'll just call it k for now, times e to the lambda t, okay? And if we think about what the derivative of x would be, so in other words x prime, then that would be, so think about this k's, those are just our constants, so we would keep those. And when we take the derivative of e to the lambda t, then chain rule would give us a multiple lambda coming out front, e to the lambda t. And remember, we are actually solving an equation of the form x prime is equal to a times x, right? So we have our derivative column vector equal to the coefficient matrix times the vector with the variables in it, okay? So if we look at this expression and we take this information and we plug it in over there, then think about what that's going to give us. So x prime would be k lambda e to the lambda times t equal to a times x, which is k times e to the lambda t. So if we take on both sides, we divide out the exponential, because that's never going to be 0 there. So if we divide that out, then that reduces nicely to k lambda equal to a times k. And then if so there are a couple of things we could do with this. I'll just go ahead and throw everything on the right-hand side. So if we subtract k lambda from both sides, then that would give us 0 is equal to a k minus, I'll go ahead and write it as lambda k. And then I guess what we could do really is factor out k, right? So in other words, we could say, well, 0 is equal to a minus lambda and factor out the k. The problem with this expression is, so think about what these are, right? A is a coefficient matrix, lambda is just some constant. So what we're really saying here, it doesn't make a lot of sense to write it this way. We're saying we have a matrix minus a constant, which we don't really work with that, right? So I think what we want to say here is we have a minus some constant multiple matrix, right? Which another way to say this, I think better, would be 0 is equal to A minus some constant times the identity matrix. Remember, the identity matrix is a matrix that has 1s on all the on the main diagonal, and then all the other entries are 0 times k here. Okay, so this is basically the nicer version of this that makes a bit more sense mathematically. So there are two possibilities here. So we have one possibility where k is equal to 0. It turns out this is a very trivial and uninteresting solution to the problem. What we're saying is all of your variables like x and y, everything is 0, and so of course when you plug in 0 everywhere, you're going to get a true statement in your system of equations. So the other more interesting thing here is looking at a minus lambda times the identity equal to 0. That's a bit more interesting. And what turns out, so this represents basically, if you think about both of these are on the left-hand side, a minus lambda I that represents a system. So what we need to do is, if we take the determinant of the system and set that equal to 0, that will give us a non-trivial solution for the system there. Okay, so what we will do, maybe I'll do this in a different color since I'm running out of room. So if we take the determinant of a minus lambda times the identity matrix and set that equal to 0, then that will give us our non-trivial solution to the system. And the values that we actually end up getting for lambda, those are going to be called eigenvalues. That will give us our eigenvalues. And so we'll do a bit more with eigenvalues and what those do and what we can use those for when we actually work out some examples, but we're going to call those values for lambda the eigenvalues. Okay, so again, just to recap, and then if you want to actually see some solutions worked and working some problems, you can watch the next couple videos. So our system is going to be, we have derivatives equal to basically some system over here involving x and y is what we've done so far. So remember, A is our coefficient matrix, it's a square matrix. X is just a column vector that has all of our variables in it. We have two types of solutions. The first one's not very interesting. When all of the variables turn out to be 0, it's a very boring solution to the system, but a solution nonetheless. The one that we'll focus on most will be the second one here, where when we look at the determinant of this a minus lambda I, set that equal to 0, that will give us our characteristic equation, which we will solve. And when we solve that characteristic equation, we will get solutions for lambda, and we said that those are going to be called our eigenvalues. So our solutions that we get for lambda are eigenvalues. With each eigenvalue, we will go back and find a vector that works to go along with each value, each eigenvalue, and the vector that goes along with that value of lambda will be called the eigenvector that corresponds to that eigenvalue. Okay, so lots of terms, lots of stuff going on, but check out the next couple examples, and I think it'll start to make sense.